and hmm? I think we haven't talked about this one yet, and also okay. So let's talk about the Firmness Principle. This is really if you have a look, wow, it's so interesting. So you can see that there is a pattern here. It seems there is a pattern here. 2 to the power n, if n is a prime number, then 2n minus 2, after you take the after you divide by n, the remainder is 0. It seems it looks like this one. But the modern computer can help you to search to find whether this statement is correct or not. So let's say if it's 3, 4, 1, then okay, then this is a common example. And then, so do we talk about this one yet? No. Yes? No. No. So the theory look like this one, okay? For every integer b, b to power p minus b, if you take them, if you divide by p, the remainder is 0. If p is prime number. The next one is if b not equal to 0, of course, divide by p, then this one will give you 1, okay? This one we call the Firmness little theorem. And then, at the end of the session. So they will try to use this theorem first, okay, before proving this theorem. Or we would like to have a look at the theorem first. Yes? So let's have a look at the proof. But the proof is not that easy actually. Wait for me for a while. Now what is stated in the theorem, right, is look like this one. B to the power p minus b is 0. If you take the remainder, if the remainder is 0. So we can rewrite the theorem look like this. This minus b if divided by p. I think it's not difficult to understand. Okay, these two are equivalent to each other. So any question here? Well, it doesn't seem like obvious. What does it mean? B to power p minus b is a multiple of p. So let's say you say k times p, okay? That means b to power p can be written as b plus k times p, okay? Then if you want the b to power p divided by p, b divided by k is not an integer, but k is an integer. So that means the remainder is this one, okay? Hmm?
Shouldn't it be B over P, not K?
Oh, B over P plus K, is it? Oh. DI. Maybe let's have a look here first. So let's have a look at these examples. Let me write down the theorem on the left hand side. Prime number P. If so for the first example, example here, this is about which statement it is, about the second statement. Okay. 2 to the power 6 is equal to 64. So if you 64 divide by 7, the remainder is 1. Okay. Obviously, you know it. And for this one, which theorem you are using? This one. Hello, hello.
The first one.
Yeah, the first one. So, and then, I think I've shown you this one, is it? They are equivalent to each other. BPU to, so it is about the first one. So then let's have a look at next one. This one, 29 is a prime number. 29 is a prime number. So, okay. So P minus 1 is 28. So he do something interesting. He make use of both theorem A and B. So let me write it down here. So you know that 2 to the power 28. Oh, no, nothing. First of all, he make use of this theorem. So if you mod 7, so this is an integer to the power 7. So what you get is 2 power 2. What you will get is, what you will get here is 2 to the power 3 to the power 4. Hmm? Oh, it's mode 5, okay? So let me write it again. So 3 to the power 28 equal to 3 to the power 4 to the power 7. Then if you mode 5, then what we will get here? Hmm? I think it's a little bit strange why it say 1 to power 7. We haven't learned about MOD yet. Oh, then you don't understand what you mean now. Actually, it's not difficult. Oh, okay. Maybe let me mention more the mean by MOD. Now, let's say if you say that M to M equal to N, okay, if you mode P. So what does it mean? That means uh, when M is divided by the N, so when M divided by P, and then the remainder is N, okay? So that means you can rewrite the formula look like this one. M can be equal to K times some constant times P plus N.
Can N be bigger than P?
No, because it's about the remainder. That means N should be smaller than P. And it should also be, it's better for this one to be positive. For N be positive, it's better, it's just better. Sometimes they write it as -1 for some field, not here. Okay, so that's why I say that this statement, now you can rewrite this statement, okay? B to power P minus B is divisible by P, okay? It means that the remainder is 0. That means it's divisible by P. So that means you can write it as K times P. So that means B to power P can be written as K times P plus B. In other words, so that means if B to power P is divided by P, then the remainder should be B, okay? That's why I say these two statements are equivalent. Any questions? No? If no
B,
question, hmm? Hmm? Okay,
I don't get it.
which one?
B to the power of P equals B. Shouldn't it be B over P?
This is about the remainder. So when you the B to power P when you divide by P what's the remainder? Now B to power P can be written as K times P plus B, okay? That means this is a quotient, is it? And then K times B, okay? Then the remainder is B. So you write B here.
All right.
Yeah. It's fine for you to divide P on both sides. But B over P is not the remainder.
Yeah.
Yeah. Okay. So then for the second for part B it say that B to power P minus 1 if you divide by P it will give you the remainder 1. It seems so odd right now because we haven't proved this theorem yet. So if you have a look at this example, it just from this one from the part B, this one from the part A. And we are going to have a look at the second example. So for second example, I'm looking at it. What does it look like? This one. Now, if you want to make use of this, the theorem part B, then you may need to rewrite the formula like 3 to the power 7 to the power 4. Okay? Because to the power 4, that means it's 5 minus 1. Then we'll give you 1 if you take the mode 5, okay? So I think there's some mistake here. I think it should say 3 here instead of 1. There is a typo, okay? I think there is a typo here. Any question? There is a typo here. Hello.
Sir, 3 to the power of 7 divided by 5, the remainder is 1.
Which one? Sorry.
So if you divide 3 to the power of 7 by 5, the remainder is 1.
No, that means the remainder is 1.
Yeah, so what is divided by what? You get 1. I'm confused.
Nah, I think the notation here is quite strange. So I think there's so many typos in this statement, okay? Let me rewrite this statement. First of all, be aware about the equal sign. If you say 60 equal 1, if you use 3 line, that means the remainder is 1 if you take the mode 7. Okay? It doesn't mean that 64 equal to 1. So this one, I think there's so many typos in this question. Now, 3 to the power 28, obviously this is equal to 2 to the power 3 to the power 7 to the power 4. Okay? And have we learned some other theorem before? Let me check. Yeah, I think we have learned the mode before. Maybe. Because I'm really bad at a number theorem. I don't think they teach some. Okay, then we skip that. We start this one. Okay. Then, if you write it like this one, now you consider this is an integer, okay? Then we apply the theorem part B. So you know this one can be written as 3 to the power 7. And then 4 can be written as 5 minus 1. Okay? P is a prime number, okay? You check it already. Then if you take the modulus 5, then it gives you the remainder 1, okay, by this theorem. So you just ignore what it is writing here. Okay. Okay.
Yeah.
Okay. So if you have a look at the next example, if you want to divide this one into divide 7 to power 200 by 23, it seems that you can't apply this theorem because 23 is obviously a prime number, but it's not 7 to the power 22. So first of all, we can still use this theorem. And then I think that it's not difficult to understand. 2 to the power 7 can be written as this one and this one. These two multiple together. The equal sign is so confusing in this note. So let me rewrite the formula. Okay. Then, if no question, and then let's have a look at the next statement.
Sir, could you explain this one? 271. I don't understand.
This one?
Yeah.
22 times 9 plus 2 is 200.
How did it get from that to 1 to the power of 9?
Yeah, I'm thinking about it also. Now we know this one. When you take the modulus and then give you 1. We may need to derive some basic rule for the modulus. So let's make it to be more. So when we say when A divided by B, okay, the remainder is R. That means we can write as this one. A equal to KB plus R, okay? And then let's say another one. Let's say if there's a B, uh, uh, when we say another number, okay? When the big A is divided by small b, okay, the same small b, the remainder is R, then we can rewrite the formula look like this one. Then, I think we can show that there's a very important or very interesting theorem. So how about if we multiply these two together and then we divide by b? What do you think? What is the remainder?
Smaller times bigger.
Yeah, small times big R. That's why it say here. So how can we show this one? So we just multiply small a and big A together, okay? So you get one term is KL times B squared times LRB plus KRB plus small r big R. Okay. I think you can see that these terms is a multiple of B. Multiple of B, small b. That means if this number is divided by small b, then the remainder should be small r big R. Okay. Any question? No? Okay, we've proved this theorem already. So maybe let me write down some maybe theorem that we may need to use later on, some equation or some formula similar to this one. So when you say A is equal to then AB will do small r, big R, okay? So how about if A to the power n? Now A to the power n can be considered as A times A times A times A for n times. That means the remainder, this remainder can be written as R to the power n. Okay. So if you understand this, these equations, and then we can have a look why it like this one. So right now, therefore I can understand this statement now. But yeah, I can understand this statement now. But let's have a look at this one. Now we know that 722 equal to 1 when you mode 23. First of all, we need to apply our theorem 1. Okay, our theorem 1. You consider this one to be A. Consider this one to be B. Okay, so a 7 squared is 49. Okay, it seems that it does not do some calculation here. It's still fine. Okay, because you can do it later on. Do you know what I mean here? Let's say okay, if you say 10 equal to 7 mode 3, it's still fine because you have made it smaller, and then it will give you the mode 4, but the remaining can be 4, but finally it can be 1. Okay, so you can do it one by one. So it does not process yet, so it gives you 49 here. And then we know 7 to the power 22 give you the remainder 1. And then we make use of the theorem 2, okay? So even you if even you it go to the power 9, if you go give you 1 to power 9, okay? So it say 1 to power 9 here times 49. Then for 49 to mode 23 it's easy, okay? You can do it by your heart. 49 minus 46, okay? So the final remainder should be 3. Any question here? No? It's already very difficult, is it? Any question?
No.
So I think you really need some time to digest it later on. Okay. Okay, maybe let's go on. Maybe, or we can take some exercise together first. Let's see if they provide some exercise in this session. Example in self-exercise here. So let's say this one, okay? Let's write down the theorem we have right now. A to power P will give you A if you mode P, is it? Another one is A to power P minus 1 will give you
1.
1 when you mode P. Now actually, if you consider carefully, this one induce this one. Do you know what I mean? Because you can write A, the remainder to be A when you mode P. So when you multiple these two together, they give you this theorem. Okay. So that means that actually there's only one statement that you need to remember. So let's have a look at this one. Office, this one should give you 1, is it? 73 is a prime number. Yeah, A can't be 0, of course. A can't be 0. But in general, we do not take A to be 0. So then let's have a look at next one, this one. 97 is a prime number. So what we need to do is 2 to the power 97 times 2 to the power 3 If you remember the remainder can be multiple together. So 2 to the power 7 when you divide by 27, they give you the remainder 2, okay? I think that's the answer already. So the answer should be 16. The next one. So you're using some similar trick, but first of all, you need to do some calculation. 1, 2, 3, 4 divided by 11 first. To get the, it can be written as 11 times 1 to 1 plus something. 1, 2, 1, 1, no, so not 1, 2, 1, 1, 1, 1, I think. 1, 1, 1, 1, 1, 1, give you 1, 2, 2, 1, okay? Then the remainder should be 13, okay? 13, or make it smaller. 11 times 112 plus 2, okay? You see? 112, 112, 1, 2, 3, 2, yeah. So it can be written as 2 to the power, actually, I like this one more, actually, because it looks nicer. I don't need to take care about the P minus 1. It's much easier to look at P and P instead of P minus 1 and P. So right now here, it is 2 to power 1, 2, 3, that is 11 times 112 plus 2, okay? That's equal to 2 to the power 112 to power 11 times 2 to the power 2. So the first one, this will give you the remainder 2 to the power 112 times 2 squared. Okay, mode 11. And then you have simplified the number already. Then what you need to do next to simplify it more. So you can write it as 112 can be written as 11 times 10. Times 2 to the power 4, okay? You put a power 2 to right here, okay? And then 2 to the power 4 can be written as 16 now, of course. And then this one can be written as 2 to the power 10 times 11 to the power 11. But if you do it like this, it takes so long time, you see? So it's better make use of the second statement because they give you the remainder 1. You don't need to simplify it more if it is the remainder 1. So capture your screen. But let's do it in another way. Then it can save us much more time. So P minus 1 is 10. So you can write it as 2 to power 1, 2, 3, 0 times 2 to power 4, okay? Then this one, the left-hand side, this one can be written as this to power 10. So when this number mode 11, the remainder is 1. So 1 times 16, then 16 divided by 11, they give you the remainder 5. Okay, so the answer should be 5. Okay. Any question? No? Now you can do it by yourself later. I'll capture the screen. Maybe let's take one challenge. Actually, I don't know if I can do it or not also. Let's have a look at question 6. So this is a plus sign here. These two numbers are multiple to, they are plus together. And then mode 13. Now, actually, I think it's not difficult to understand. If A is, the remainder is small r, the big A that give you the remainder big R. So what is the remainder when these two numbers add together?
Small r plus big R.
Yeah, it should be small r plus big R. I think it's easy, is it? Not difficult to understand. So then, we can do it one by one actually. So we make use of this theorem, okay? A to power p minus 1 and then mod p. So 1, 1, 1, 2, 2, 2. So make use of this one. P is 13. So that means you need to make this to be power of 12. So this one can be written as 12 times. You may take out your calculator. What's the 18? Okay, 18. Then
18 and 6, right?
okay. So you can write it as to power 18 to power then to power 12 times 11 to power 6. Right, 111 to power 6. Then if you take the mode, it will give you this one equal to 1 times 111 to power 6. Right now you move to mode 13. Now this is still a very, very, very large number. So how would you do it? Mhm. So how will you do this one? Although we have simplified the case to this one. Yeah. So
Since 111 is wait 8 7 mod 13,
plus
so
20. No, it's 8. Okay.
7 mod 13.
No, 7 40 13 is 91.
No, I mean the remainder is 7.
Why?
No,
Oh,
no,
when 11 divided by 111 divided by 13, they give you the remainder 7.
7. So 7 to the power of 6. That's much simpler.
Yeah. So you make use of that. What we have told you, okay? So 111 and then you take the okay, 111 give you the remainder 7 when you mode 13. You can check it, okay? 8 times 13, they give you 104, okay? Then it should be 7 to the power 6. But this is still a very large number. Well.
And then you can go like 49 to the power of 3 and then go, you know?
Then right now you can still simplify it a little bit, by a little bit, okay? 49 to divide by sorry, 10 to the power,
Remainder is 10, right?
okay. And then okay. Then no, I don't think any film can help you right now. It's just 1013, okay? Then you can do it by yourself. Okay. You just stop at this part, okay? No. Eh? No. I'm poor in calculation. Okay. 12? Yeah, I think it's 12. Yeah, 12, okay. So, and then you can do this one also, okay? Then you can, I think then you can get the answer. If no question, then wow, it takes us so long time to talk about the Fermi's theorem, but we haven't showed how this theorem is proved. Eh? Hmm? 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 Okay, then let's have a look at proof of this theorem. But the proof seems a little bit complicated also. They just want to show this theorem, okay? They just want to show this one. If this one has been shown, that means A and B have been shown, have been proved already. So let P to be a prime number by the binary coefficient. Now this one is CPJ, okay? CPJ. Now office there you can see that J is smaller than P, okay? By definition. J is more than J is more than P minus 1 here. Then what you can see that is that P is a prime number, but in the numerator there is no factor of P. J is smaller than P. Okay, J is smaller or equal to P minus 1. That means J is smaller than P. Then J factorial don't have a factor of P. Okay, even you multiple all the terms, okay, because P is a prime number that is larger than J, that means the multiple of the J factorial have no factor of P. I hope you can understand this one. So does P minus J factorial. So that means that the whole fraction has a factor of P. Then if you mod P, then give you the remainder 0. That's it. So we prove this one. And then you can rewrite the terms like this one. Okay. They just told you how to prove it. Okay. Then we go on to Firmness Principle. Actually, they make use of the remainder theorem. So they they're using the mathematical induction to prove this statement. I think let me have a look. So since this statement B can be 0, but obviously if B is 0, then this statement is always true. Okay? Then next consider when B is not equal to 0. Then if B is not equal to 0, so and then let's try to get when P to 1, and then 1 to the power P that is equal to 1 will give you the remainder 1 when you divide by P, okay? So when P to 1, the statement is true. But let's say when so this is B, okay? So let's say when B equal K, and then we assume that the statement is true, okay? Assume this is true. Then when B equal K plus 1, if this statement is also true, then by mathematical induction, this theorem is correct. So let's see, okay, let's expand this one. K plus 1 to power P. I think you know how to expand this one. And then the last term is this one. Okay, so I'll just copy from here. So what does it mean here? Now, if you still remember, we have proved this theorem, this one. So let's say if J is in between P minus 1 and 1, and this they will give you the 0 when you mode P. If you have a look here, this one contains the term P, CP1. That means it has a factor of P. Up to this term, there is also a factor of P. So everything in between is a multiple of P. So what is left? K is left, K to power P and 1. So when K to power P is mode P, by assumption, what we have assumed, and then it shows that it is K. So that gives you that K plus 1 to power P, when mode P, they will give you K plus 1. Therefore, the statement is also true when K equal K plus 1, but when B equal K plus 1. Then by mathematical induction, the statement is always true for all integer K. If you haven't learned about the mathematical induction, then I don't know what I can help. And then we may need to have a look at another statement, another proof here. Okay. So we have proven this statement already using the mathematical induction. But if you haven't learned about the mathematical induction, then let's have a look at the second proof. So it starts with the following lamina. Let P not equal to 0. The set of this number contains each non-zero congruence class and P exactly ones. Well, I think this proof is more difficult. Maybe you skip this proof, okay? Or if you don't understand the mathematical induction, then either you learn it or ignore the proof. Then let's go on to the earliest theorem. Okay. Now, for the earliest theorem, I think it's much more difficult. So maybe let's put it in the next lesson. And then you can see there are so many strange symbols. So for the remaining time, let's do some exercise. I'm not sure if you have tried to do some exercise in the file that I have sent you. Where's the file? Let me download it first. So let's try to do some mathematics question instead of the programming questions. Oh, this one. I think this one, even you list out all the possibility, all the numbers together, I think it's still not that difficult. So what I will try to do first of all, I will try to list all the prime numbers. So first of all, is 1 a prime number?
No,
No.
because by definition, a prime number has to be bigger than 2 or equal to.
Yeah. So 1 is not a prime number. So all the prime number, let's list them out first, okay? 2, 3, 5, 7. I think you should all know how to write down very fast. Okay. So, and then if you have a look there, 2 can never form a pair that is with another prime number, such that it will divisible by 4. Okay, because 2 is an even number, all the others are odd number. The sum of odd number plus and a even number will give you an odd number. That will not be a multiple of 4. So I may just do it by writing down. Okay, 3 can, okay, 1. I think this it's not too slow. Okay, then okay, let's go on 3 and 7, and then 3 and 11. Eh, yeah, 3 and 5 and 19. Okay, then go on. If you can think of any other method, then please let me know. 7 and 13, 7 and 17, okay, 2. Then 11 and 13, 1, 2. 13 and
11 and 17. That's 28.
yeah, so 2 here. 28 is a multiple of 4. 13, 13. Okay, 1 here. Okay, and then 17 and 16 a multiple of 36. Okay, so add them up together. 6, 12. The answer should be 12. Okay, not difficult. Okay, not really difficult. Okay? Even you can do it when you are in primary school. So let's have a look. This one. This is what? Hmm? There are n stones on the ground. They take turns to pick at least 1 stone, up to 10 stones each time. Oh, this kind of trick. This is about the game theory. I don't think we have time to talk about this one. So the one picking the last stone always win. Do you know why? Hello? Oh. They take turns, then n stones on the ground. They take turns to pick one as 1 stone, up to 10 stones each time. So either picks stone first, the one picking the last stone win. This one actually is about the number theorem. Then first of all, well, I've learned it before, but I forget how to do it in a more smarter way. Even if I teach you, and then it's really a long lesson. So you make use of your wisdom to think about this question. So you may first of all think about the last step first. So let me give you some scenario, okay? Let's say if there are 15 stones at first, okay, 15 stones. If you are Ada, how many stones will you take in the first step? Hello, 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 hello. Hello.
10.
10. If she take 10 stones, then 5 stones left, and then a Bob can win.
Oh, wait.
Or
4 stones, okay? If he actually there's some 4 stones. So if Ada take 4 stones, that means there are 11 left. Okay? Even Bob take 10, there's still 1 stone left. Or if the Bob take 1 stone, and then Ada can there are 10 left. Okay, that means Ada can take the remaining stones. Okay. So if Ada take 3 stones first, so there are 12 stones left. And then if you are Bob, how many stones will you take?
right? You lose anyways.
Yeah, no, Bob can win if Ada take 3 stones first. So Bob should take 1 only. Okay. Then Bob can win.
Right.
Mm-hmm. So actually, you may need to think about the case for the last step first. Then you try to make up some rules for this game. I forget. It seems it's about the multiple of 9. I forget about it already. So maybe you can try to make up some. Because for 1027, it's impossible for you to think about it. But for 30, okay, it's still fine. It's not a large number. But let's say if the this is 30, okay. So can Ada win? So we all hope that 30 Ada will lose because we can choose the answer C directly. If not, okay, then so sad. So let me write down, okay, how many he takes and how many left. Okay. So if Ada want to win, that means he take the stones at last. That means she should take either 1 to 10 stones, okay, at last. So that means how many left in the last step. So it should left 1 to 10 stones, okay? That means if you take the sum of the stones that have been taken here, I don't know if there are enough steps or not. It doesn't matter, okay? The sum here should be uh, 20 to 29, okay? Do you understand this one? So do you think Ada can win? What do you think about it?
No, he can't win.
Why?
Wait, let me think. Okay.
Or you take some time to think it again at home, okay? And maybe try to sort out one solution for this one. And then if not, okay, let's take the screenshot. And then I'll search the theorem behind in the game theorem. So otherwise, we need to use this kind of method. So let's see. This question, okay? How many pieces do you need to cover each square in 5 times 5? I think you can try to. The thing is, this is really not a difficult question. You can just try to do it one. Let me draw it. Plus 1 plus here, okay? But this method is not too good. Not really good. I guess 7, okay? But that means the answer can be 6 also. But you may need to see if you can cover them all by 6 plus sign. I don't think so, maybe. Or let me do it again. So this is a plus sign. Oh, I don't think so. No. Still need 1, 2, 3, 4 more actually. So actually you can try by error, okay? Although there may be some mathematics behind, but it's easier for you to do it like this one. So maybe, okay, we finish the lesson today now, and then let's have a lesson on next Tuesday, okay? So we can start to do some exercise together. Yeah, we can start to do some exercise together. Okay. No question? No question, then bye bye lah. Bye bye. Bye bye. Bye bye.
Uh,
Bye.